From guiding transatlantic flights to pinpointing your nearest coffee shop, the Global Positioning System, or GPS, underpins an astonishing array of modern life. It's a technology we largely take for granted, yet its operation is a triumph of physics and engineering. Many assume GPS functions by simply measuring distance, but investigative reports and scientific analyses reveal a far more intricate truth. Its core mechanism is predicated on incredibly precise timekeeping, not direct measurement. This fundamental principle, as asserted by engineers at the U.S. Naval Observatory, dictates that GPS relies on knowing the exact moment a signal leaves a satellite and the exact moment it arrives at your receiver. At the heart of GPS lies a vast network of orbiting hardware. As of late 2023, the U.S. Space Force, which operates GPS, maintains an active constellation of 31 operational satellites. These spacecraft orbit Earth at an altitude of approximately 20,200 kilometers, 12,550 miles, completing 2 full orbits every day. The design, as detailed by Lockheed Martin, ensures that at any given moment, a minimum of 4 satellites are visible from virtually any point on Earth's surface, a critical factor for accurate positioning. This redundancy, built into the system since its inception, minimizes signal obstruction issues. The extraordinary precision of GPS hinges on the timekeepers aboard each satellite. Every GPS satellite is equipped with multiple atomic clocks, typically rubidium and cesium standards. According to reports from the National Institute of Standards and Technology, these clocks are accurate to within a few nanoseconds. To put that into perspective, an error of just 1 nanosecond can translate to a positional error of about 30 centimeters, roughly 1 foot, on the ground. Maintaining this level of accuracy, despite the harsh conditions of space, is a monumental engineering feat, demanding constant calibration and monitoring from ground stations. Here's where the narrative gets truly mind-bending. Einstein's theories of relativity are not just theoretical constructs but practical necessities for GPS. First, special relativity dictates that clocks moving at high speeds run slower relative to stationary observers. GPS satellites, moving at approximately 14,000 kilometers per hour, 8,700 miles per hour, experience this effect. As calculated by physicists at MIT, without correction, their onboard atomic clocks would appear to run about 7 microseconds per day slower from Earth's perspective. This seemingly small discrepancy accumulates rapidly, leading to significant positional errors if unaccounted for. But that's only half the story. General relativity, Einstein's theory of gravity, introduces another critical time distortion. It predicts that clocks in stronger gravitational fields run slower than those in weaker fields. Since GPS satellites orbit at a significant distance from Earth, they experience a weaker gravitational pull than receivers on the planet's surface. According to data from the European Space Agency, this means their clocks run approximately 45 microseconds per day faster than identical clocks on Earth. These two relativistic effects, acting in opposite directions, must be precisely balanced for GPS to function. When combining the effects of special and general relativity, the net result is that GPS satellite clocks gain about 38 microseconds per day relative to clocks on Earth. This isn't just a curiosity for physicists, it's a fundamental design challenge. Engineers at the U.S. Naval Observatory state that without incorporating these relativistic corrections, GPS would accumulate positional errors of roughly 10 kilometers, 6 miles, per day. To counter this, the satellite's atomic clocks are deliberately calibrated to run slightly slower on the ground before launch, ensuring they tick at the correct rate once in orbit. This pre-calibration is non-negotiable for accuracy. Each GPS satellite transmits radio signals that contain precise timing information and ephemeris data, a kind of almanac detailing the satellite's exact orbital path. These signals travel at the speed of light, approximately 299,792,458 meters per second. Your GPS receiver on Earth merely listens for these signals. It doesn't send anything back to the satellites. When a signal arrives, the receiver records the precise time of arrival and compares it to the time the signal was transmitted, which is encoded in the message. The difference in these times, multiplied by the speed of light, gives the pseudo-range to the satellite. To determine your position, a GPS receiver employs a technique known as trilateration, often mistakenly called triangulation. It's not about angles, but distances. With just one satellite, your receiver knows it's somewhere on the surface of a sphere centered at the satellite. A second satellite narrows your location to the intersection of two spheres, forming a circle. A third satellite reduces this to two possible points on Earth. The fourth satellite is crucial. It not only resolves which of the 2 points is correct, but also synchronizes your receiver's less precise internal clock with the highly accurate atomic clocks of the satellites. This clock synchronization is vital for accuracy. Despite the system's inherent precision, various factors can introduce errors. One significant challenge is atmospheric interference. As GPS signals travel from space, they pass through the Earth's ionosphere and troposphere, layers of the atmosphere that can delay and bend the radio waves. The ionosphere, with its free electrons, can slow down the signal, while the troposphere, containing water vapor, can also cause delays. According to NASA, these atmospheric delays can introduce errors of several meters. Researchers employ models to estimate and correct for these delays, but variability in atmospheric conditions means absolute prediction is impossible. Even with meticulous engineering, perfect accuracy is elusive. Minor imperfections in the satellite's reported orbital data, known as ephemeris errors, can translate to positional discrepancies on the ground. While ground control stations constantly monitor and update these orbital parameters, minute deviations can occur. Furthermore, despite the incredible stability of atomic clocks, small drift errors accumulate over time. The U.S. Naval Observatory reports that these clock errors, combined with orbital inaccuracies, are typically corrected daily but can still contribute to a few meters of error. The interplay of these factors necessitates continuous adjustments and refinements. The receiver on your device also introduces its own set of potential inaccuracies. The quality of the antenna and the processing capabilities of the GPS chip can influence performance. A phenomenon called multipath error occurs when a GPS signal bounces off objects like tall buildings, mountains, or even the ground before reaching your receiver. This creates an indirect, longer signal path, leading the receiver to miscalculate the distance. Urban canyons, for instance, are notorious for exacerbating multipath errors. According to surveying experts, these reflected signals can easily add errors of several meters, making precise urban navigation particularly challenging. Historically, there was a significant distinction between military and civilian GPS accuracy. Initially, the U.S. government implemented selective availability, deliberately degrading civilian GPS signals to limit accuracy for non-military users. This policy, in effect from 1990, typically reduced civilian precision to within 100 meters. However, President Bill Clinton ordered its termination in May 2000, citing the increasing reliance of civilian applications. As reported by the White House, this decision immediately improved civilian accuracy to 10 to 20 meters. Today, both military and civilian users generally benefit from similar levels of accuracy, though military receivers can access encrypted, higher precision signals for specific applications. To further enhance accuracy and reliability, particularly for critical applications like aviation, augmentation systems have been developed. The Wide Area Augmentation System, WAAS, in North America, for instance, is operated by the Federal Aviation Administration, FAA. WAAS utilizes a network of ground reference stations that precisely monitor GPS satellite signals. These stations calculate the exact errors caused by atmospheric conditions and other factors, then transmit correction data to geosynchronous satellites. These satellites, in turn, broadcast the corrections to WAAS-enabled GPS receivers, reducing errors to typically less than 3 meters horizontally and 3.5 meters vertically. This level of precision is crucial for precision landing approaches. Another form of augmentation is differential GPS, or DGPS. This technique employs a ground-based reference receiver at a precisely surveyed location. This reference station calculates the GPS errors it experiences and then broadcasts these corrections to other nearby DGPS-enabled receivers. Unlike WAAS, DGPS corrections are typically localized, offering very high accuracy within a regional coverage area, often down to sub-meter levels. NOAA, which operates some DGPS services, highlights its use in maritime navigation, precision agriculture, and surveying. The trade-off is the need for local infrastructure and a shorter range of effectiveness compared to wide-area systems. GPS is just one component of a broader family of technologies known as Global Navigation Satellite Systems, or GNSS. While GPS is operated by the United States, Other nations have developed their own independent systems. Russia operates GLONASS, the European Union has Galileo, and China maintains BeiDou. India's Navi-C and Japan's QZSS provide regional augmentation. According to a 2023 report from the European Global Navigation Satellite Systems Agency, most modern receivers can now utilize signals from multiple GNSS constellations simultaneously. This multi-constellation approach significantly enhances accuracy, availability, and reliability, especially in challenging environments like urban canyons, by providing more visible satellites. Each GNSS system has distinct characteristics. GLONASS, Russia's system, offers similar global coverage to GPS but has a slightly different orbital architecture. Galileo, designed by the European Union, aims for superior accuracy, particularly with its public regulated service, and is fully civilian-controlled. China's BeiDou, originally regional, completed its global coverage in 2020. While all systems rely on similar fundamental principles, differences in signal structure, orbital altitude, and onboard clock types create unique performance profiles. A comparative analysis by the U.S. National Coordination Office for Space-Based Positioning, Navigation, and Timing indicates that a multi-GNSS receiver can reduce typical errors by 30 to 50% compared to using GPS alone, illustrating the benefits of diversity. The evolution of GPS is ongoing. Modernization efforts by the U.S. Space Force include deploying newer satellites with enhanced capabilities, such as the L5 signal. This third civil signal, broadcasting on a protected aeronautical frequency, offers improved accuracy and robustness, especially crucial for aviation safety and autonomous vehicles. The L5 signal is anticipated to become fully operational across the constellation by the mid-2020s. Furthermore, research by Stanford University indicates that integration with 5G cellular networks and other terrestrial positioning systems promises even greater precision and reliability, particularly in urban areas where satellite signals can be weak or obstructed. The drive towards ubiquitous positioning continues. Beyond personal navigation, GPS has become an indispensable economic driver. According to a 2019 study by the National Institute of Standards and Technology, NIST, the economic benefits of GPS to the U.S. alone are estimated at $1.4 trillion, with an additional $37 billion annually. Its applications span agriculture, enabling precision planting and harvesting, logistics, optimizing delivery routes, financial transactions, providing precise timestamping, and emergency services, aiding rapid response. This unseen infrastructure, born from Cold War necessities, now powers global commerce and human connection, making it one of the most impactful technologies of the last half-century. Its subtle complexity belies its profound influence. Our deep dive reveals GPS not as a simple distance calculator, but as a masterpiece of applied physics and global cooperation. It's a system where every nanosecond, every relativistic adjustment, and every atmospheric correction is critical. While remarkably robust, its reliance on highly precise timing and vulnerable satellite signals underscores its fragility. As we continue to integrate GPS and other GNSS into increasingly critical infrastructure, understanding its intricate mechanisms, inherent limitations, and ongoing evolution becomes paramount. The invisible network above us is a testament to human ingenuity, constantly striving for ever more accurate, ever more reliable positioning on our dynamic planet.